and welcome to this video. Today I will try to break down a fascinating questions and some pretty deep theorems and proofs, such that they should be understandable if you still have some knowledge of high school level mathematics. The question itself is geometric. The main tool we use is Combinatorial, but we will even touch on some linear algebra, number theory, and polynomials in between, which make this a beautiful proof sequence in my opinion. Feel free to pause the video and rewind to fully convince yourself of some things. And for this, it also might be useful to use a pen and paper. Since the best way to understand mathematics is actually to do mathematics, there will be some questions that you can answer and prove yourself if you want to. With all this, let's now get started. So we'll formulate the problem into how many parts do we need to partition an object to make it smaller. Well, what do we mean by smaller? Smaller by area or volume? Then always just two parts are enough. So this is a pretty non-interesting question. But if we mean smaller by diameter, this becomes much more interesting because it's actually a quite difficult question to answer. As a reminder, we define the diameter of an object as the maximum distance between any 2 points on that object. And as another reminder, the distance between 2 points, x, y, we view them here as vectors in n-dimensional space, is x minus y in the dot product with itself and then the square root of that. And if you look at this in 2 dimensions, this might remind you of the Pythagorean theorem, and in 1 dimension it's just the absolute value of x minus y. But yeah, this is how it's defined for higher dimensions. Okay, so let's now think about the easiest cases first. In 1 dimension, we just have line segments, all our objects, and maybe unions of line segments and so on. And then we can quite easily imagine that we can just find a point in the middle, split the line segment or the line segments in half, and then the 2 line segments now have a smaller diameter than the line segment before. Okay, now let's move on to 2 dimensions. Here we have a circle. And here I want you to work out why splitting a circle into 2 parts always results in at least one part having the same diameter as the original circle. But as we can see here, splitting it into 3 parts actually, again, reduces the diameter. So we can see this here is the diameter of this part, and this is, of course, smaller than the diameter of the entire circle. And now maybe think about how this would look like in 3 dimensions. If you have a sphere, is it enough to partition a sphere into 3 parts, or do we need to partition it into 4 parts? Well, with all this, here we always need one more part than the dimension. We can form a conjecture, and this is actually Borsuk's conjecture. So if we take any object, a subset of the R to the n, with finite diameter, and then we can always partition it into n plus 1 parts. This is what this means, such that the diameter of the entire set is always strictly bigger than the diameter of any of our parts in our partition. Well, let's first ask, can we do better? So for this, the answer is no, via the simplex. Because, I mean, it could be we've only now checked dimension 1, 2, and 3 in our head, maybe. That for dimension 10, we only need 10 parts and not 11, as our conjecture would claim. But we can disprove this with the simplex. In 2 dimensions, this is just the equilateral triangle. In 3 dimensions, it's a tetrahedron, as seen here. And we can define it as such that it includes the points 1 plus square root of 3 divided by 2 in all entries, and then 1 in one entry and 0 in all other entries, and all combinations of that. And then it's quite easy to check that the diameter of the simplex is square root of 2. And the distance between any of those 2 points is square root of 2, and we have n plus 1 points, with n being the dimension. So if we partition the simplex into fewer than n plus 1 sets, then one of those sets will contain 2 of those points. So this set will then have diameter square root of 2, and yeah, thus we need a larger partition. Okay, now so our conjecture looks pretty good. It's tight if we consider the simplex. And it has actually been proven for n being in 1, 2, and 3, so up to 3 dimensions, and also for smooth convex sets. What those are isn't important right now. And was actually widely believed for 60 years, and there have been some attempts to actually prove it entirely. Yeah, so for 60 years, mathematicians thought this to be true until it got disproven in 1993. Yeah, that's the problem. Borsuk's conjecture is wrong. And it's actually spectacularly wrong. And in this video here, we will construct a counterexample in the R to the 15,375. So in over 15,000 dimensions, we will create an object that disproves Borsuk's conjecture. You may think that this is now useless because, I mean, we move around in 3 dimensions and we can barely imagine 4-dimensional objects. Well, computers, for example, the device you're watching this video on, they use even more dimensions than what this object here resides in. So high-dimensional vector spaces are actually quite relevant, even in applications. Well, now about this object that we'll construct, we can't visually think about it at all. And because of this, we approach this geometric problem with now combinatorics, which is the mathematics of counting. And here we have a combinatorial theorem, which we'll prove. Don't worry if all of those symbols are unfamiliar for you, we'll go through each of them. So first off, this bracket n is the set 1, 2, all the way up to n. And yeah, prime numbers you should be still familiar with. It's just those numbers which are only divisible by themselves and 1 isn't a prime number. So 2, 3, 5, 7, and so on. Then next up, 2 to the power of this bracket n is now the set which contains all possible combinations of numbers from bracket n. So, and f, which we call a family, is a subset of 2 to the bracket n, which is denoted by this symbol, the subset. So with only this condition, and let's say n equals 4, we might have that our family looks like it's the set of the set 1, 2, the set 1, the set 2, 3, the set 1, 2, 3, 4, and the empty set. Again, the empty set is also included in 2 to the bracket of n, because here we choose the combination of not taking anything. The next up, this absolute value of x is actually the cardinality of x, which denotes the number of elements inside a set x. So here we actually restrict that for all sets in our family, they have cardinality 2p minus 1. 2p minus 1 elements, thusly. And this cap here is the intersection. So this x intersects y includes all elements which are both in x and in y, and no others. And then, of course, here we have the size of the intersection. So what this basically states here at first, that we have p being a prime number, then we have a family of subsets of numbers up to n. All of those sets in our family have size 2p minus 1, and they can't share exactly p minus 1 elements in common. And then the statement of the theorem is that such a family can have at most the sum from I equals 0 to p minus 1 of n choose I elements. Okay, and this is the is-in symbol. Okay, the reminder for this statement, what this bound means. Here, n factorial is n times n minus 1 all the way to 1. And n choose I is the number of possible choices of I elements from an n element ground set. And this is defined also as n factorial divided by I factorial times n minus I factorial. You can think about why this is true. And then this is the sum symbol, this big sigma. So we take the sum of I equals 0 to p minus 1 of n choose I. And this is what it would look written out. Okay, now what does this actually say? Is there any strength to the theorem? Well, actually, this bounds the size of a family by n choose p minus 1 asymptotically, and this is very small when compared to n choose 2p minus 1. If we fix the p and increase the n. Because n choose I is maximized if I is roughly n divided by 2. So it gets larger for large n if we increase the p, and here we have double the p. So this is actually a very strong bound, and we get this just from this intersection property. Again, this here is the size of f if we did not have this property. In that case, we just have our n-element ground set and all possible choices of two p-1 element sets. And this property here is also asymptotically tight, so we can't find a much better bound. If we just let, for all sets X and F, let all of them include the numbers 1 up to P, then the cardinality of a set of a family F would be n choose p-1, because all of the sets would contain all the elements up to P, and then p-1 others, which we can choose here. And then we would fulfill this property with the intersection size, because all of the sets in our family would intersect already in those P elements, so it's impossible to have this intersection size p-1. Okay, now for the proof. For each set in our family, we construct a vector Vx, which is a binary vector, so it is only made up of zeros and ones to the power of n. And it's the characteristic vector. It has ones at all of the positions where it includes an element, and 0 at all the other positions. So for example, V of the set 2, 3 is equal to 0, 1, 1, here at the second and third position, and 0 everywhere else. And then we also define polynomials for each set X in our family, Fx, that are defined on this binary vector space. We prove that those polynomials are linearly independent and bound with the dimension of the function space. Okay, if you're not familiar with those two terms, I'll explain them now. So linear independence you might have heard of with vectors. Well, we can actually view polynomials as vectors in a way. So here we have f equals 3x squared plus x, g equals x squared plus 3x, and h being 4x squared plus 4x. Then this here is f, this here is g, and this here is h. And we see that f plus g is h, if we just do it algebraically, but also geometrically, if we take the vector g and go to in the direction of f, with the length of f to there, we are at the position of the point h. So there is basically a bijection between polynomials and points in this coordinate system. Now, f, g, and h are linearly dependent because f plus g minus h is equal to 0. So we can combine them in a way to get 0. And this works algebraically, but also, again, here geometrically. Now, in the converse, if we choose f hat to be x squared, g hat to be x, and h hat to be 1, then they are linearly independent. You can see them here in the coordinate system, because we can't combine them in any way to get 0, neither here geometrically nor algebraically, by multiplying them with some numbers and adding them together. And now I want you to think about why this is true. If we have degree k polynomials, then at most k plus 1 of them can be linearly independent. Okay, next up we'll need to talk about the ZP field. You might be familiar with this symbol. This is just the symbol of the whole numbers. And now ZP includes all of the numbers, of the positive whole numbers, up to p-1, and it includes 0. Now, so still 1 plus 1 is equal to 2 in this ZP field, so things behave normally somewhat. But now what happens if we go over 10? Well, then we go back, so you can imagine this like a clock. So 2 plus 10 is not 12 as in the whole numbers, but 1. So if we go over 11, we always subtract by 11. And 11 here is the same as 0. Now, why do we have now a prime number here? Why is this relevant? Well, if you imagine the normal clock, so we have a 12 here, then waiting 3 hours 4 times, so 3 times 4 is 12, gets us back to 0. So 3 times 4 is 0. And we don't want two positive numbers multiplied together to be equal to 0, because that's very weird. That doesn't work like that in the whole numbers. So that's why we choose ZP with P being a prime number. Then this can't happen, because prime numbers are only divisible by themselves and 1. So in ZP, the product of two positive numbers, so two numbers which are not 0, is again another number which is not 0. Okay, now let's get to the actual proof. We define fx going from 0, 1 to the end to this ZP, which we just discussed, and define fx of v as the product from I equals 0 to p minus 2 of the sum from j in x of vj in brackets minus I. Okay, now what does this mean? So this is just here the product sign. So we're writing this polynomial as a product of terms, of sums specifically. Now this sum over the j and x of vj, since we are just in the binary vector space, we either have a 1 here or a 0 here. And we have a 1 here if vj has a 1 here and a 0 otherwise, but we only sum over those indices which are in our set x. So we can imagine that if we plug in a characteristic vector vy, which only has 1s at those positions where it includes the elements, then this here is exactly the intersection size. Because we only get a 1 here if this position, this element is included in the set x, and it's included in the set y, since otherwise we'd have a 0 here. So this here is actually our intersection size, and then we do minus I, and I goes from 0 to p minus 2. Okay, now what happens if we plug some vector in? Let's say we plug a vector in with the intersection size of x and y being p minus 1. Well, then, since I only goes up to p minus 2, all of these terms in the product are positive, so we get some positive number in the ZP. And this also happens if the intersection size is 2p minus 1. This only happens, since all our sets have cardinality 2p minus 1, if x and y are equal. Since 2p minus 1 in ZP is the same as p minus 1, since we already then reduce by p. Okay, but now what happens if the intersection size is any other number? So, for example, the intersection size is 0. Well, then this here, the intersection size minus this equals 0. So we have a 0 term in our product. So the whole thing is 0. And this not only goes up to p minus 2, but also then after, for numbers larger than p minus 1, intersection size is larger than p minus 1. Since we're living in ZP, that is the same as those intersection sizes from I equals 0 to p minus 2. So the intersection size of p plus 3, for example, in ZP, this is the same as the intersection size of 3. So we get another 0 term here in the product. So we have the statement, those polynomials of a set x, when taking a vector of a set y, is only a positive number if the intersection size is p minus 1, or the intersection size is 2p minus 1, and it's 0 otherwise. And since we've excluded the intersection size p minus 1 in our family, this can only happen if the intersection size is 2p minus 1. And this can only happen, since all of the sets have size 2p minus 1, if x and y are the same. Okay, let's now take a linear combination of all our polynomials in our family, of the sets in our family. So we multiply them with some number for each set. And we try to get this to equal 0. Okay, now if we evaluate this entire thing at Vx, then everything is 0, as we've discussed earlier, except Fx. Fx of Vx is something non-zero. So all we're left with is a lot of 0 terms, because Fy of Vx is 0 if x is not equal to y, and then just alpha x times Fx of Vx. And since Fx of Vx is non-zero, alpha x has to be 0. And then we can iterate this argument for all the members x in our family and get that all of the alpha x have to be 0. And thus we've shown that our polynomials that we've just constructed for our family are linearly independent. Now, what do our polynomials look like? They're of degree at most p minus 1, since our product here has only p minus 1 terms, and is in n variables, since we're going from this binary vector space in dimension n. And since this domain is binary, vi is the same as vi squared, is the same as vi cubed, and so on, since 1 squared is 1 and 0 squared is 0. So all polynomials are multilinear, so we just have v1, for example, here times v2. Another term could be just v6, another term could be v3 times v1 times v10, and so on. So this is what our polynomials might look like. And thus, we can think about this, that our function space has the dimension of exactly this, the sum going from I equals 0 to p minus 1 of n choose I. Why is this? So our polynomial consists of terms. Each of those terms has between 0 and p minus 1 variables, and they're just multiplied together. And those variables are chosen from the set n, since we're going from dimension n. And thus we've achieved a bound on the dimension of a function space. And since we can only have as many linearly independent polynomials as the dimension of a function space, and we have exactly as many linearly independent polynomials as we have elements in our family, we can bound the size of our family by this dimension. Okay, now from this we get a corollary that if we choose n as 4p, so if we look at the last theorem, then the cardinality of f divided by 4p, choose 2p minus 1 is smaller or equal to 1.1 to the negative 4p. So this here again is the size of a family which does not have this condition and then contains all of the elements of size 2p minus 1 in our 4p element ground set. So this indicates inverse exponential behavior, that just by this, excluding this one intersection size in our family, the relative size of this family to the family where we don't have this condition decreases exponentially. Okay, for this proof, we use that n choose k times k divided by n minus k plus 1 is n choose k minus 1. You can work this out pretty simply. And then we have cardinality of f is smaller or equal to 4p choose p minus 1 all the way to 4p choose 0. And then we can apply this and do some bounding. So 4p choose p minus 1, our k here is our p, and then we can approximate all of these terms by 1/3, and then apply this iteratively to get 1/3 squared, and so on, all the way to from 4p choose 0 to get to 4p choose p. We have to multiply with at least 1/3 to the power of p. And yeah, so we get another bound of 4p choose p times this sum of powers. And this is just a geometric sum, something you can also look up. And this actually evaluates exactly to 1/2. So we can bound the cardinality of a family to 1/2 times 4p choose p. Okay, now if we divide by 4p choose 2p minus 1, then we have 1/2 4p choose p divided by 4p choose 2p minus 1. Then if we put everything in, some terms cancel, and then we have just these factorials. And then if we think about these factorials, for example, the 3p factorial, we can cut that off at the point 2p plus 1 factorial, since all of the terms cancel there. And the 2p minus 1 factorial, we can cut this off at the point p factorial, since all of those terms cancel off that, so we get something of this form. And then we can see that each of those terms is smaller or equal to 2/3. So we can finally get this elevation that this fraction is smaller or equal to 1/2 times 2/3 to the power of p minus 1, and we can approximate this by 1.1 to the power of negative 4p. Okay, now let's finally get to our disproof of Borsuk's conjecture, which was given by Kahn and Carlyle in 1993. The statement is actually quite strong and states that if p is a prime number and n, the size of our partition, is smaller than 1.1 to the power of 4p, then there exists some object x in the r to the 16p squared, so in this dimension, such that for all partitions of x into m parts, there exists some part of our partition which has the same diameter as the original object. With this, we get the smallest counterexample, p being equal to 31, and thus our dimension are in 15,000. If we optimize some constants and so on using the proof, we actually get disproof in r to the 1,000. But the important thing here is that the conjecture is exponentially wrong. So we assumed a linear behavior, that we always can find a partition of size n plus 1. But here we need a partition of size roughly equal to 1.1 to the square root of n. And this makes a huge difference. So if we have n being 1,000,000, which is not a prime number, but we can find a prime number close by, then we need more than 10 to the 41 parts by this theorem here, instead of the million parts, which we assume with our conjecture. Okay, in preparation for this, we define this cross product with a circle around it. So we take some vectors in the R to the n, and then we define this x cross circle y to be simultaneously a matrix and a vector in the R to the n squared. They're kind of isomorphic. If you're familiar with this notation, it's basically the product of the two vectors x times y transposed. But we can more simply think of it that it has entries xi times yj. So we have two indices, and at indices ij, it has the entry xi times yj, where I and j are the indice entries in our x and y, which are in the R to the n. Yeah, and we simultaneously view these things as not just matrices, but also vectors with a dot product. And just a reminder, the dot product between two vectors is just the sum over all indices of xi times yi. And then a small theorem that we need, a small lemma if you want, is that for all x and y in R to the n, x, and we'll call this tensorization from now on, tensored with x, dot product y tensored with y is the same as x dot product y squared. And this is quite simple. We can just write this out, and then we have the sum going from, for all I and j going between 1 and n, of xi, xj times yi, yj. Then we can separate these, and then this is just the same. So it's a sum squared, and this is just the dot product. Okay, now let's get to the actual proof. We let n equals 4p, and our ground set A be, our family A be the numbers up to n, and then all the 2p minus 1 element subsets of that. And now for each of those sets in A, again, as a reminder, they're subsets of the numbers from 1 going to n, and we choose just exactly 2p minus 1 of those numbers. We let Vx be the sign characteristic vector. We've seen the characteristic vector before, but now it's signed, so we have a minus 1 if some element, so some number is not in X, and a 1 otherwise. So for example, the V of just 1 has a 1 in the first position and minus 1s in all other positions. And then we define for each X also a Ux, which is Vx tensorized with itself in the R to the n squared. And then we view our object A hat being the set of all Ux, where X is in our original set A, or family A. And this is actually the object where we'll disprove Borsuk's conjecture. Okay, but first we'll have to show that now the cardinality of our A hat is the same as the cardinality of our A. For this, we just show that there's a function, there's a bijection. So we get from each element, from each set in A, we easily get the sign characteristic vector. And from the sign characteristic vector, we directly get our Ux vector in A hat. But now, how do we get from our Ux vector in A hat back to the set? Well, we see that the 1j entry by our tensorization, and this definition here, is equal to Vx1, so the first entry, and the j times the jth entry of Vx. And thus, if we just view the first column of Ux, so just Ux1, it's Vx1 times Vx, so the entire column here. And thus, the entire sign characteristic vector is the first column of our Ux divided by the first entry of our Vx. Now, we don't know that first entry, but we do know that summing up over all entries of Vx always gets us -2, because all of the sets X are 2p minus 1 subset of a 4p element ground set. So we have 2p minus 1 elements which are in our set, and 2p plus 1 elements which are not in our set. And thus, we can always look at Ux, its first column. If it has more -1s than 1s, then this is just exactly Vx, and Vx1 is equal to 1. And if not, we can just multiply with -1, and then we get also Vx. And with this, we have a bijection between A hat and A, and thus their cardinalities are the same. Okay, now what are the distances in our now weird geometric object A hat, which is in the dimension r to the n squared? Well, let's take some vectors, some sets x and y and A, then ux minus uy and the distance squared. We can just multiply this out as ux minus uy dot product ux minus uy, and multiplying this out as ux dot product ux plus uy dot product uy minus 2 ux dot product uy. And then we can put in our definition for the u, which are just the vx tensor with themselves. And then we can apply our theorem we had before, or small lemma, and get that this is all equal to vx dot product vx squared plus vy dot product vy squared minus 2 vx dot product vy squared. Now vx dot product vx, there, since vx and vx are equal, and they just have -1 entries and 1 entries, we always have 1 times 1 in each entry, or -1 times -1 in each entry. Both are equal to 1, and we're summing up over n entries, so this is just n squared. And the same goes for this, so we have here this distance squared being equal to 2n squared minus 2 times the dot product of vx times vy squared. Now, what is this? Here we have a visualization, so this is the entire ground set n, so all the numbers up to n. This is our set x, this circle, and this is our set y. Then vx dot product vy is equal to x intersects y, so this is this intersection, since there vx and vy both have 1s. So 1 times 1 is 1. So here we have this many 1s that we're summing up. Then plus, this is just all the elements in our set n without all of the elements which are in x and y. That's what this means. So this is basically everything that's not in x and y, because there both x and y have -1s, and then again there we are summing up over 1s because -1 times -1 is 1. But then we have -1s at all of the positions in the dot product. We have 1 times -1, or -1 times 1. So where we have an element that's in x but not in y, or an element that's in y but not in x. Those are these here. Okay, and now we can see that the cardinality of this set here, so all of the elements which are neither in x nor in y, is equal to n minus cardinality of x minus cardinality of y, but plus cardinality of x intersects y, since if we take all of the elements and take away some elements in x and the elements of y, we're basically taking those elements which are both in x and y away twice, so we have to add them once. And then we see that minus x minus y minus x without y minus y without x, this is just minus 2x minus 2y. You can think about this visually here. And with this, we finally get that vx dot product vy is equal to 4 times x intersects y plus n minus 2 cardinality of x minus 2 cardinality of y. But we, of course, know the cardinality of x and the cardinality of y. It's just 2p minus 1. So this whole thing is equal to 4 times cardinality of x intersects y minus p plus 1. We can plug this back into our distance squared here, and then we get that for any two sets in our family, the distance between their vectors and this a hat geometric object is 2n squared, this distance squared, of course, 2n squared minus 32 times cardinality of x intersects y minus p plus 1, and this whole thing squared. Okay, now let's think about this. The distance here is maximized if the intersection size is equal to p minus 1. Why? Because then here we have p minus 1 minus p plus 1, so this is 0, and then the distance is 2 square root of 2 times n, which is actually the diameter of our a hat set. But if we have any other intersection size, then this here is something positive, and then we or something negative, either one, then we square it, so it's something positive, and we do minus, so we get a smaller distance. So we can say that a subset b hat of our geometric object a hat, so maybe a partner partition, has a smaller diameter if and only if all of the intersection sizes of the corresponding vectors ux and uy and b, if then x intersects y, the kernel of that is not equal to p minus 1. Because if in b hat there are some ux and uy such that x intersects y is equal to p minus 1, then diameter of b is again square root of 2 times n, since this here is then 0. Okay, and with this we can finally apply Frankl-Wilson. So we choose a family such that the intersection size p minus 1 is avoided. Then the cardinality of A divided by the cardinality of B by our corollary is larger or equal to 1.1 to the 4p. And thus we get the result that any partition of A hat, our geometric object, into fewer than 1.1 to the 4p parts yields a set B in our partition, or B hat in our partition with corresponding vectors x and y, such that the intersection size is p minus 1, and thus the diameter is the same as that of the original object. And this finally disproves Borsuk's conjecture. Okay, now with this we've shown that roughly 1.1 to the square root of n is a lower bound to Borsuk's partition problem. But we can also find an upper bound, and this is kind of left here as an exercise. This is a proof via spheres, so we show that this partition size is always enough. So we just take any object in the n-dimensional space with a finite diameter, and then I want you to find these, or select these C1, C2, C3, such that we have a good proof here. And then we find a maximal set of points I, which have pairwise distance at least C2 times D. And thus the spheres around our points I and I with radii C2 times D cover X. Because if they wouldn't, then we'd find another point in our maximal set of points, which has a larger distance to the other points than C2 times D. And then we put other spheres around our points with radii C1 times D. And these are now disjoint by choosing our C1 carefully. And they're all covered by another sphere with some center V and radius C3 times D. And then we just show with this calculation that we can bound the cardinality of I by putting C1 divided by C3 to the power of n to the other side. And this here is just an argument over volume. So the volume of the smaller spheres which are disjoint, and this is the value of the volume of the large sphere, which covers everything. And yeah, with this you can show that this maximal set of points, you have a bound for it, an upper bound, so it's smaller or equal than something. But you've also shown that the spheres with radius C2D cover the entire set, and thus you can turn this into a partition. And they all have smaller diameter by choosing C2 smaller than 1. Yeah, if you optimize the constants in the last proof, you get a bound of 5 to the power of n plus 1. I think you can bound of 9 to the power of n is more easily achievable. And in general, for this problem, the best known upper bound is the square root of 1.5 plus O of 1, is just a small value to the power of n. And the lower bound, which we've seen before, was 1.1 to the square root of n, has been improved to 1.225 to the square root of n. So not a big improvement. And with this, it's completely open what the asymptotic behavior is like, because this here is exponential growth in the square root, which is far slower than here exponential growth with just linear, so no square root. And again, just plug this into the calculator, you get wildly different values for large n for this. So this is still a topic which needs a lot of research. And you, as a lucky viewer, might be one of those who contributes to this. Okay, thank you for watching the video. Here are my sources, and I hope you have a nice day.